Alright, good morning. This is Math 125 Statistics. Today we're going to talk about Section 4.4, the multiplication rule, the basics. This actually used to be two sections in an older version of the text. This newer version has separated this topic of the multiplication rule into two sections, 4.4 being the basics and 4.5 being a little more advanced in heart. Alright, so we're going to talk about the basics of the multiplication rule today. Let's see where we've been in Chapter 4, Section 4.2. We talked about basic probability, and that shouldn't have been too tough. And then 4.3, of course, we talked about the addition rule. And we learned that the addition rule is invoked in OR-type events, or events linked with an OR-type statement. Today we're going to start talking about the multiplication rule, 4.4 multiplication rule. Let me write that down again. Multiplication rule, the basics, and the multiplication rule is invoked in AND type situations. Much like the addition rule will connect with the word OR, the multiplication rule will connect with the word AND. Alright, what we're going to seek here in Section 4.4 is probabilities of this type. Probability of A and B. In other words, the probability that event A and event B are occurring. And we'll make this a little more formal. We'll say the probability of A and B is the probability that event A occurs in a first trial. Write that down. Probability that A occurs in a first trial in some experiment, and that event B occurs in a second trial of an experiment. Alright, so then we can ask ourselves, what is the probability that A and B happen in both of those trials? Alright, motivation. Let's motivate our lecture today with an example. Let's take a two-question quiz. Let's say some teacher presents you with a two-question quiz. Let's say the first question is true or false, and the second question is a multiple choice with 5 choices. Okay? If a student knows nothing and picks randomly, on both questions, let's find the probability that both are correct. Okay, that is our goal here. Well, I can translate that into an AND statement. That's the probability that the first question is correct, and the probability and the second question is correct. Let me be sure to say that correctly. This is equivalent to the probability that the first question is correct and the second question is correct. And that's our goal here. Alright, what I'm going to do is draw a tree diagram of all the possible responses here. And you may remember this from Section 4.2. Let's say we've got a first question and we've got two possibilities for the first question. Let's say the first question is a true-false question, all right? And then we've got other possibilities for the second question. I think you'll agree that each of these true-false possibilities tails off to 5 other possibilities in the second question. And as we know, every possible path from left to right gives me another possible outcome. So I go from true A, true B, all the way down to false E. And I think we can see we've got 10 possible test papers, 10 possible outcomes if a student picks randomly on both questions. Alright, now out of these 10 possible outcomes, only one has both questions correct. Write that down. Only one outcome has both questions correct. We're not sure of the actual outcome, but we can be sure that only one has both correct. So if I ask then what's the probability that both correct, that the first one is correct and the second one is correct, I can say, well, there's 10 possible outcomes. Only one of those outcomes is correct, and I end up with a probability of 0.1. Alright. Let me suggest you a shortcut rather than writing out the tree diagram, which can get very tedious very easily. Let's say here the probability that the first is correct and the second correct. Let me propose to you a little shortcut, which I'm sure most of you can see already. I claim it's the probability that the first question is correct times the probability that the second is correct. Let's see if that works out. Well, what's the probability that the first one is correct? Remember, the first question is true-false, so that's going to be a 1/2 probability of being correct if picking randomly, and the probability that the second one is correct is in 1 out of 5 or 1/5, and of course I get the same answer, 1/10 or 0.1. This suggests a rule for AND-type probabilities, or probabilities of AND-type events. Let me claim this. The probability of event A and event B equals the simple product of the probabilities of the two events. This is my multiplication rule for independent events. Let me write that down. Multiplication rule for independent events. Okay. Now, let me describe what I mean by independent events in this above example. I think you'll agree that the probability of the true-false question being correct is independent of the probability of the second multiple choice question being correct. That describes the heart of what it means to be independent. Perhaps we can make this a little more formal. Events A and B are independent if the occurrence, it should be a U there, if the occurrence of one of the events, either A or B, does not affect the probability of occurrence of the other event. Okay? So events A and B are independent if the occurrence of one does not affect the probability of occurrence of the other, and if they're not independent, well, I suppose we can call them dependent. And I think we'll batter around both of these words interchangeably. Not independent, of course, means dependent. Alright, so we've got the multiplication rule for independent events. What about dependent events? And I'll give you kind of a classic example of what we mean when events are dependent. I want to look at that lie detector matrix again. I'm citing example 1 in our book, example 1 on page 161 in section 4.4, multiplication events, the basics. And remember the lie detector data? We betted this about a good amount in section 4.3, our previous section. Lie detector study. You may recall in this study, I'll summarize the data. Well, remember we had liars, which I will signify with a cap L, and not liars, which I will symbolize with a L bar or not L. And we had people with a positive result, in other words, the machine said they lied, and people with a negative result, meaning the machine said they did not lie. And let me fill in the numbers. You're probably very familiar with this data, hopefully. And recall the grand sum was 98. We had 98 total subjects in this study. Alright. Let me say in this study of 98 lie detector subjects, I'm going to randomly select 2. And here's a key word here, a key phrase. I'm going to say without replacement. That means you pick one person, you don't throw them back in the pool for another possible choice, and then you pick a second person. Alright, let me pose this question to you. What's the probability that the first one got a positive test result? In other words, the machine said they lied. And that the second person got a negative test result. In other words, the machine said they did not lie. Alright, well, without replacement means these probabilities are dependent. Because if I don't replace the first person into the pool for a possible draw in the second trial, I'm affecting my probabilities down the line. What I'm going to do here is say, well, it's much like the first example we talked about here. It's the probability that the first is positive. Let's get that first. Well, how many positive results do we have here? It looks like 57 over 98. And I'll multiply by the probability of the second event, but again, we're doing this without replacement, so I've got to adjust my available pool. Instead of, because the first one is not replaced in the pool, I've got 97 to choose from now. And out of those 97, how many of them have a negative test result? Looks like 41, right? The sum of that row is all those who had a negative test result. Alright, so by making a slight adjustment to the multiplication rule, I can grind out and the probabilities even when events are not independent or dependent. Alright, I'll plug this out, and I get 0.246 as my final probability. Let me write this down. In dependent events, basically I do still multiply the probabilities of the individual events, but I've got to adjust the pool size for the second, third, and even more events down the line. In dependent events, we must adjust. Let's adjust for, well, here it was a second trial. Alright, I'll leave it like that. In dependent events, we must adjust for the second, third, or even fourth, fifth, sixth trial. Okay? Alright, I want to look at an example, another example in the book. This is example 2 on page 163. I've got 5 pacemakers. You might want to refresh your memory on that. Let me see. Can I read it here? It is kind of a wordy example in the book. You might want to pause. You might want to pause and read this problem, example 2, page 163. Alright, quality control in manufacturing. Alright, the long and short of it is, for this experiment, we've got 5 pacemakers. 3 of them are good, and 2 of them are defective. Okay? Part A asks, randomly select 2 with replacement, and Part B says pick 2 without replacement. So let me write that down. I'll pick 2 with replacement, and Part B will pick 2 without replacement. Okay, scroll down here. Alright, we want the probability that the first, well, let's see, in Part A, let me write this out. I want the probability that both are good. Alright, let me work on Part A and I'll come back to Part B. Remember, Part A is with replacement. With replacement is kind of a code word meaning independent trials or independent picks for each pick. Right? In other words, probabilities are not affected down the line. Alright, the probability that both are good, I can rewrite this as the probability that the first is good and the second is good. Okay? Well, by the multiplication rule, I can say it's the probability that the first one is good times the probability that the second one is good. Well, of course, in this small pool, we got the probability the first is good is going to be 3/5. And with replacement, meaning the probability of the second one being good is going to be the same as the probability the first one is good. So no adjustment needed here. I end up with 9/25, which of course decimalizes to 0.36. And let me put a little box around that. Alright, so that wasn't too tough. Now Part B. We want to randomly select 2 without replacement. That means your probabilities are going to be affected down the line. And that's kind of a code word for dependent picks. Or dependent probabilities down the line. So in Part B, we also want the probability that both are good. Alright, I claim that's, let me rewrite it here. It'll be a little more formal here. Probability that the first is good and that the second is good. I claim that's really the product, very similar to Part A. But this second probability has to be adjusted. I'll just write the word adjust there with an exclamation point, because without replacement your available pool is affected down the line. So what's the probability that the first one is good? Well, we still got 3 good out of 5. What's the probability that the second one is good? Again, without replacement, you've got 1 less available in the pool to pick, and you've got 1 less good one to pick also. So 3/5 times 2/4 now is going to reduce to, well, of course, it's 6/20, or 0.3. I'll call it 0.30. So you can see that the probabilities change whether we do or do not have independent or dependent events that we're describing the probability of. Okay? I want to do a homework problem, somewhat similar. Let me get a fresh screen here. I believe this is in your homework list. This is number 14 on page 168. And let me turn there myself. On page 168, polygraph test. Okay, it refers to that polygraph data. I'm going to write down this table again. Again, we've got some people that lied in this study, some people that did not lie in this study, and we've got some people that the machine detected a lie and the machine did not detect a lie. Alright, so our familiar data is stated in what they call the chapter problem. Alright, let me read the problem. If 3 of the 98 test subjects are randomly selected without replacement, find the probability that they all had false positive results. So we're going to randomly select 3. Out of the 98, recall the grand sum for this experiment was 98. And they are selected without replacement. Now remember, without replacement is our clue that we have not independent situations in these events. In other words, we've got to affect our probabilities, adjust our probabilities as we go down the line. Alright, so the probability that, let's see, we want the probability that 3 had a false positive. That's what the textbook is asking for. So that's the number we need. Well, what is a false positive? In other words, you did not lie, but the machine said you did. Right? So actually, those are the false positives. There's 15 people out of these 98 had false positives. Alright, now we want the probability that 3 had the false positives. Well, I claim it's the probability that the first had a false positive times the probability that the second person chosen had a false positive times the probability that the third person chosen had a false positive. Now again, we must adjust both numerator and denominator as we go down the line because we are making these selections without replacement. Alright, what's the probability that the first one has a false positive? Well, that's going to be 15 people out of 98. Alright. Now, without replacement then, what's the probability that the second one is a false positive? Well, we've got one less person to choose from, and we've got one less false positive to throw in the pool. And similarly, what's the probability that the third one is a false positive? Well, again, assuming the first 2 have been picked without replacement, we've got 96, 2 less to choose from, and 2 less false positives to choose from. And if we grind that out, I get a very low probability of 0.00299. Now the book goes on to ask if this is unusual. Now you may remember from section 4.2. We didn't talk about this in class, but we did talk about it via the homework problems. And the guideline is an event is unusual if its probability is less than 0.05. 0.05 represents a 1 in 20 chance of happening, and certainly this number here is less than 0.05. So by this guideline, I claim this is an unusual event. So the 3 randomly selected people having a false positive is unusual by this guideline. Okay? Alright, so we've got a good foundation in multiplication rule, the basics of it. I want to talk about a couple more subtopics before we call it a day. And the book makes let's see. The book makes an issue about this idea here. Let me write it down. When is it okay to treat dependent events as independent? Well, I think you'll agree that treating events as independent shortens your work quite a bit. You don't have to keep knocking down numerators and denominators as you trail down the line. Well, it turns out you can treat dependent events as independent. I claim this is okay if the sample size is no more than 5% of the population from which it's drawn. Alright, let's do an example of what this means. I'm going to look at number 29. This is on page 170 in your text. Alright, I'm going to read the problem. Let's see. Defective tires. The Wheeling Tire Company produced a batch of 5,000 tires that includes exactly 200 that are defective. Alright, so we've got 5,000 tires. 200 are defective. And that means 4,800 are good, right? By deduction, right? If 4 tires, part A, if 4 tires are randomly selected for shipment to an outlet, what is the probability that they are all good? Alright, so let's see, what's the I'm going to randomly select 4. Find the probability that all 4 are good. That is our task in part A. Alright, now notice, and I think the book does this purposely, they don't specify if these 4 are selected with or without replacement. Okay, the kind of implication is that they are without, but they don't really say. Let me do this problem both ways. I'll say without replacement and with replacement. I'll grind it out both ways. One's certainly going to be easier to do, one's going to be a little more difficult to do. Well, the probability that all 4 are good, again without replacement, well, I've got 4,800 good ones to pick from out of 5,000. And remember, without replacement means dependent events, so you've got to knock down, well, in this problem, both your numerators and denominators as you go down the line. Run out of room very quickly here. 4797 divided by 4997. Alright, if I punch this out, and very tedious to enter this in on your calculator, I think you'll agree, I get a point. Again, the calculator gives us 10-digit accuracy. I'm going to go ahead and write down the full accuracy that the calculator gives us for reasons that'll become obvious in a minute. Alright, so this is part A done with the assumption of no replacement. Okay? That's our final answer for part A. Now I'm going to do it with replacement. Alright? The probability that all 4 are good in this situation, well, if I assume that we're doing it with replacement, that means all the trials are independent. As we go down the line, the probabilities don't change. So really what I'm doing is saying the probability that the first one is good times the probability that the second one is good, times the probability that the third one is good, times the probability that the fourth one is good. It's just that same fraction being multiplied by itself 4 times. A little less ink and a little less button pushing on your calculator. And if I punch this out, I get 0.849346560. And I think you'll agree with me that these answers are very, very close, almost to the point of it would be splitting hairs to assume no replacement here. And much easier to do assuming there's a replacement, and you get an answer virtually identical to the answer that you get assuming no replacement. Alright, so the idea here, it's okay to assume independent trials, right? Independent trials. Again, if your sample size, the book's guideline says, if your sample size, and the sample size here was 4, is no more than 5% of the population from which it's drawn. That's what they call the 5% guideline. Write that down. 5% guideline. So don't make more work for yourself than you have to. If you can justify this statement, it's really going to save you a lot of button pushing and ink on test day or homework day. Alright, here in this example, the sample size was 4. We randomly selected 4, and 4, of course, is not more than 5% of the 5,000 tires from the available population. Right? 5% of 5,000, and let's say 10% is 50, so 5% is going to be 250, way more, or I should say way not more than 5% of 5,000. Okay? Alright, one more problem I want to talk about before we call it a day. This is example 6 on page 166. Let me turn there myself. Redundancy for increased reliability. You might want to pause and turn there, familiarize yourself with the problem statement, then come back. Redundancy for increased reliability. Modern aircrafts are now highly reliable. One design feature contributing to that reliability is the use of redundancy, whereby critical components are duplicated so that if one fails, the other will work. For example, single-engine aircraft now have 2 independent electrical systems so that if one electrical system fails, the other can continue to work so that the engine does not fail. For the purposes of this example, we will assume that the probability of an electrical system failure is 0.001. Alright, pretty clear problem. Let's look at, we are asked for parts A and B. Part A. If the engine in an aircraft has one electrical system, what is the probability that it will work? Well, that's pretty soft. They want the probability that you've got one electrical system. What's the probability that the engine works if you've got one electrical system? Well, I claim it's 1. Take away the probability that the electrical system fails, right? It is possible the engine, well, if you only got one electrical system, if the electrical system fails, the engine will not work. So I'll just take 1 minus the probability that it fails. That's 1 minus 0.001. They give you that in the problem statement. The probability of one electrical system failure is 0.001, and that leaves us with a very high probability of 0.999. Right? The engine will work with one electrical system with a probability of 0.999. Alright, Part B is a little more interesting. It says if the engine in an aircraft has two independent electrical systems, what is the probability that the engine can function with a working electrical system? Alright, so let me scroll down here in a fresh screen. We want to look at Part B. We want two independent electrical systems in this plane. Two independent electrical systems. Okay? We want the probability that the engine then will work. That's what we seek. Well, what's the probability that the engine will fail? Well, the engine will fail if both electrical systems fail. And we've got two independent electrical systems, and for this engine to fail, both of these electrical systems will have to fail. Alright, well, that's going to be the probability that the first fails and the second electrical system fails, connecting it to an end type event by the multiplication rule. These are independent events because the electrical systems are explicitly told to us that they are independent. It's the probability that the first electrical system fails times the probability that the second electrical system fails. And the probability of one electrical system failing is 0.001. Alright, so I just multiply 0.001 by itself, or just square. So 0.001 times 0.001, of course, gives me 0.000001. Or 1/millionth, right? 1/1,000,000th of a chance. Alright, that's the probability of an engine failure. But the problem asked us, what's the probability that the engine works in the case of two redundant electronic systems? So the probability that the engine works is going to be 1 minus the probability that the engine fails. And that's, of course, going to be 1 minus 0.000001. And that, of course, is 0.999999. That's our answer to Part B. And, of course, we can see the probability goes up from Part A. Let me refresh our memory. From Part A, with one electrical system, the probability that the engine works was 0.999. In Part B, we had two redundant, independent electrical systems. Let me write that down. Two independent electrical systems. And that probability is 0.999999. Notice the probability goes up. This is closer to 1. The answer to Part B is closer to 1 than the answer in Part A. So certainly by adding independent electrical systems, we increase our probability that the engine works. Alright, there's homework problems that kind of extend this idea, so I'll leave those for you. This concludes, let's see, we're approaching the 40-minute point, so this will conclude our lecture on 4.4 multiplication rule for basics, and that is all for today.